One way to get around this invertibility problem is not to think of the entire sine function, starting at 0, going up, then going back down again, but rather to look only at part of the domain of sine of x. And we can actually give this limited window version of sine almost the same name. We call it capital sine of x. This is not going to be a major thing, but just if we ever need to distinguish them. Capital sine of x is exactly the same as the sine graph, except all we do is define the function only from negative pi over 2 to pi over 2. And that covers the range of y values of negative 1 to 1. So we have one complete range of outputs in this part of the cycle of sine of x. If we define this capital sine of x, it does have an inverse function. If we go back for a moment, this function here certainly does pass the horizontal line test. No matter where we draw a horizontal line, we only get one value back. And that's our recipe, or our hack, to allow us to create an inverse. Because we have passed the horizontal line test by truncating our function, we can now draw an inverse function. And it's worth noting what that, again, comes from. This graph here is made from reflecting the graph of sine of x, which goes like this, across the y equals x line. So there's that reflection to construct the inverse function, where we essentially replace the roles of x and y in our formula. And the same thing on this side. How do we describe this function with notation? One is the notation that is on your calculator, sine negative 1 of x. The one we're going to try to use preferentially is arcsine of x. So this arc here indicates an inverse. And it's very, very important to recognize that this is one whole word, indivisible. It's not x run through a sine function, then run through an arc function. It's not that. Arcsine is all one word. You can use either of these notations as you go through the course. We are going to generally stick with this notation here because we find it less ambiguous than the negative 1 power. Quick check on fundamental properties for functions. What's the domain? Again, domain is the range of, shouldn't use the word range, it's the list of acceptable inputs to arcsine. And if we think about what arcsine does, it takes ratios and gives back angles. Just like the sine function takes angles and gives back ratios. So if we think about possible ratios, arcsine has a domain of possible ratios of opposite over hypotenuse, and that gives us a range of negative, or domain rather, of negative 1 to 1. And you can see that in the graph. If we look at the black line specifically, that's the graph of the inverse sine or the arcsine. It's only valid from negative 1 input to positive 1 input. The range is the list of possible outputs. And here we have angles coming back. And because of the way we've defined this restricted interval for the sine function, we can go from angles of negative pi by 2 up to pi by 2, and that's about it. You can certainly memorize these properties. I find it more helpful simply to remember what the idea of the arcsine function is to take ratios and go back to angles based on the sine function, and then think of how we define that transformation based on this limited interval for the sine function, starting at negative pi by 2 for inputs, pi by 2 for outputs. When we do the inverse, that becomes the output, and the ratios become the inputs. That's a graphical way of looking at sine and arcsine's relationship. However, we can also look at it formulaically. And this is one of the classic inverse relationships, again, like the exponential and logarithm. If we have e to the ln of x, we take the logarithm, then we use the exponent, we get back to x. The same thing happens with sine and arcsine. If we start with x, take the sine function of that, and then take the inverse sine of that, we get back to x. There's a little more fine print on this, that these values have to be in certain ranges, but otherwise this relationship of starting with a value, applying one function and then its inverse, and doesn't matter which order we do that in, gets us back to the original value. We're going to see the fine print in action though. Let's try this first. arcsine of 0.5. There are two straightforward ways to answer this problem. One is to use our calculator. And if we do that, again, keeping ourselves in radians, we get that arcsine of 0.5 is approximately 0.524. Another way, though, is to draw a triangle. And if we draw a triangle, what we are saying is that sine of something is equal to 0.5, and if you like, we can restructure that as 1/2 or 2/4, whatever we like, but the key thing is the ratio of the sine function, which is opposite over hypotenuse, that is going to be a ratio of 1 to 2. So say that's our angle on this side, doesn't matter where we define it, as long as they're consistent. The opposite side to the hypotenuse side will be 1/2. And actually, as soon as we draw that, we recognize our old friend, the 30-60 triangle. And this angle gives us the narrow angle there, which is pi over 6. And if you do a quick calculator correction on that or check on that, we find that pi over 6 is in fact 0.524, etc. So direct calculator version or the exact version based on one of the special triangles. It's unfortunately not quite always that easy. Let's take a look at the sine of this angle here, which gives us a ratio. If we want to go backwards and say, what's the angle that we would get with a ratio of 0.951? Again, we'll try our calculator. And if we do that, we get a value of 1.256 radians. And you notice this is not equal to what we started with over here, negative 7 pi over 5. But we said the sine of that angle was that ratio, so why, when we do the inverse, do we not get back to where we started? I think the easiest way to see this is to look back at our sketch of the sine function. So if you have a sine function and its relationship with the input angle, let's call that x here, we have a ratio of 0.951, and that's the ratio that goes up on the top or the vertical axis here. But what we're saying in this scenario is we have an angle of negative 7 pi over 5 would actually be back here and giving us a ratio of 0.951. So sine of this value is this y coordinate. However, because of the way the restricted domain works, we're only allowed to give, when we go backwards, values that are between negative pi over 2 and pi over 2. We're only allowed to give answers for the arcsine that lie in this interval here. Where does that lead us? Well, if we continue on this 9.51 value, 0.951, we can also find another x value where we get the same coordinate or the same y value, and it happens to be our 1.26256 here. So this value, sine of that, is 0.951. Sine of this angle is 0.951. Sine of a bunch of things is 0.951. But there's only one inverse relationship. There's only one inverse value that we're allowed to use because only one value will lie in this domain here. Now it is worth noting that we can even get more precise. Knowing all of this background, we don't have to settle for decimal values for this particular angle that we're looking for. We can actually note that we have a reference point here. We're at negative pi. This would be negative 3 pi over 2 at this point here at the peak. And negative 7 pi over 5 isn't quite that far. What we get when we look at that peak there, we actually get some symmetry with the peak over here. This distance back between these points will be the same distance here because the sine function has this nice regular structure to it. And if we start asking ourselves how far apart are these two values, this coordinate here at 3 pi over 2 at the peak, and the one we started at, the negative 7 pi over 5, that, if we do a bit of math, that's 15 pi over 10. Let's write that out. This one here is, of course, negative 14 pi over 10. And the difference then is 1 pi over 10, or just pi over 10. Well, the same thing's going to be true on this side. If we talk about the distance between these 2 points, it will be 1 pi over 10 as well. What's the reference point? We're at pi over 2 or 5 pi over 10. And so if we back off this much from here, the angle we're looking for, theta, will be the 5 pi over 10 backed off by pi over 10. That'll be 4 pi over 10 or 2 pi over 5. There's other mental math tricks you can use for this. We went into a little more detail here for those who are a little less familiar with it. But at the end of the day, we get 2 pi over 5. And if we want to confirm that that matches our earlier calculator work, we calculate literally 2 pi divided by 5, and we get 1.256, etc. radians. In terms of student expectations, we would expect students to be able to manipulate a sine graph, or for some students it's easier the unit circle. In any case, whatever technique you like, to get back to exact values for this kind of problem.